Hello, welcome to Technical Founders. My name is Carlos Lara, engineer and entrepreneur, and this video is an introduction to limits and derivatives in calculus. Calculus is the mathematical study of change. Everything in the universe is changing. Everything in life changes. And calculus is a language used to quantify those changes, to make predictions about what's going to happen in the universe, in life. There's so many different applications of calculus. So starting with a simple function here, we have y equals x squared. And y and f of x the same thing. So we have a function of x, f of x, x squared, a parabola. And here we've only drawn one quadrant for simplicity. And if you want to calculate how much that function is changing, let's say from x equals 2 to x equals 3, what you have to do is calculate the slope of the line here. And it's simple algebra, and I put the equation here. And it's simply the difference in y minus divided by the difference in x. So that's how we calculate the slope, and that's how much the function changed between those 2 points. And visually, this would be a straight line going from across this point and this point. So we call it the tangent line here, the slope. But let's say you are not satisfied with the average. Suppose you want to know how much the function x squared is changing at every point along the curve, at every point along the function. In mathematics, we say that a quantity is infinite if it is arbitrarily large. And we say that a quantity is infinitesimal if it is arbitrarily small, so very close to zero. So let's say you want to calculate how much this function is changing. Let's say from this point 2 plus another point 2 plus 0.00001, like a number very, very close to zero, but it's not zero. But it's just an infinitesimally small change in x. Like just in that very, very tiny interval. And why? What is the value of the slope? How do you do that? And this is where the magic of calculus comes in, the miracle of calculus. So here we have the general form of writing the slope of a line, which is, and here I drew another graph here with an arbitrary function. And so we have f of x plus delta x, and then f of x here in the y, and then we have x, and then x plus delta x. So this change here was delta x, and this is some delta y. So in general, we have y2 minus y1, so f of x plus delta x minus f of x, and then x2 minus x1. So x plus delta x minus x, so the x cancels, so that's why I only have the delta x here. So that's the general form. So now with calculus here, here's what we can do. We can say what happens if this delta x gets arbitrarily close to zero, becomes infinitesimally small, this quantity delta x. And so here, for example, the distance between these 2 points will start to shrink. So this point will, for example, travel down, and then it'll get very, very close to that original point. So here here's where the concept of a limit comes in. So in calculus, we have limit as delta x goes to zero. So basically, we're letting delta x shrink, get very, very small, so close to zero, arbitrarily small, and then we want to calculate the value of the function. And this limit, as delta x goes to zero of the slope, because we have the general form, this creates a new function, and we call this the derivative of the original function, f prime of x. So we have f of x, our original function, and then we have the derivative of the function, f prime of x. And usually, actually, how we write the derivative of a function is we say the derivative with respect to x of f of x. And again, it's a new function that is basically the measure of how much the original function is changing with respect to x. And it doesn't have to be x, you can have t for time, for a real world application, for example, but this is how it's working mathematically. So let's go ahead and compute this function that we have here. We have our f of x is x squared. Let's plug it into here. So let's see. So we have f of x plus delta x. So we'll plug in x plus delta x in the x squared. So we have limit as delta x goes to 0 of x plus delta x squared minus x squared, right? Because x squared is our function, is our f of x here. And then this we will divide it by delta x. This will be equal to limit as delta x shrinks to 0. And here it's just we simply multiply this out. So here we would get x squared plus 2x delta x plus delta x squared. Actually, I run out of room here, minus x squared, and then all of it divided by delta x. So the x squares cancel, so you have x squared minus x squared, so they cancel. So we have limit delta x goes to 0, and we have 2x delta x plus delta x squared here divided by delta x. And the delta x, you can hear the division, they cancel here. The numerator, each term has a delta x, so one of these cancel and these cancel. So we have limit as delta x goes to 0 of 2x plus delta x. So what's happening here? Delta x is going to 0. So what's happening to this quantity? It's getting smaller and smaller and smaller. It's approaching 0. So this becomes 0 here. So we have that the derivative with respect to x of our function x squared equals 2x. And look, this is a function of x. This is what we also call f prime of x. So the derivative of the function, this measure of how it's changing along every point on the line, creates a new function, the derivative of the function. And notice that it's not like it was initially. It's not a quadratic or here a square function. Here it's actually a linear function. So the function is different. And so this is how you would do it manually, just so you know how it's working, the limit. But I will give you in this introductory video a simple formula for how to calculate the limit. This limit as delta x goes to 0 of a simple quadratic function. In this case, we have x squared, but we can have other different kinds of quadratic function. We can have a polynomial, for example. We can have x cubed plus 2x squared plus x plus 1. And in that case, you would take the derivative of each term in that sum individually and just add them up. So that's how we would do it. So in general, the derivative with respect to x of x to the n, quadratic function here like this, very simple, would be n x to the n minus 1. So what happened here? We grabbed the n, the exponent, and we brought it down in front and multiply it in front. And then we subtracted 1 from the exponent. So we decreased the exponent by 1. So let's do it for our example here for x squared. So we have the derivative with respect to x of x squared is equal to, so what do? We grab the exponent and we bring it down to the front. So we have 2x and then 2 minus 1, because n minus 1, so we have to the 1. And we don't really need to use the 1 here because it's implied that it's 1. We don't need to write it. We have 2x, so it matches what we had before. So that's a very simple way, and we'll get into more detail in future videos how to do different kinds of derivatives. But this is a very simple example, a very simple explanation of how limits work, what they're used for to measure the change of a function, and not the average change, like we said before, between two specific values, but the change at every single infinitesimally small point along the curve, for every infinitesimally small change in x, and all of those changes, the value of the slope at each line, that creates a new function, which is the derivative of the function. And we call it a limit also because this quantity, the slope of the line, is approaching a limit at each point. It's approaching a specific value. And we'll get into convergence and divergence. Sometimes it may not approach any value. Sometimes it may become infinite. right? The function may become infinite when doing a limit, but we'll get into that in future videos. So thank you for watching. Questions, thoughts, comment below, and I'll see you next time.